Okay, so this is 5.5, applications of vectors. We're gonna do a few applications of vectors that you'll find similar ones in the homework. The way we're gonna do these applications is heavily skewed toward using trig to work them out. If you do see these types of problems involving vectors in the future, perhaps in a math class or in a physics class, it's very likely they'll do them in a slightly different way, where you're working kind of more naturally with vectors, because all of these problems you can work out just doing the algebra of vectors. But since we're a trig class, we're going to reduce them to trig problems as much as possible. So just take note of that if you do see these similar problems in the future. You can look at them in either way, but ultimately, I think the vector point of view, where you just work with vectors natively in a way, is a better point of view, but it requires a little bit more technology, a tiny bit more technology than we have in our class, a tiny bit more mathematical technology, as in you probably want to understand a little bit more about the dot product, and then you'd want to introduce something like the projection vectors and stuff like that, which we don't want to do. So we're going to focus on setting these problems up, right? They're going to involve vectors, of course, but ultimately we're going to reduce them to trig problems. All right, so I've written down a first example here. We have the resultant of a 10-pound force and another force has a magnitude of 12 pounds at an angle of 20 degrees with the 10-pound force. So first of all, we see the word resultant. That means we're adding two forces, right? Remember, the resultant is another way to say the sum of two forces, especially used in physics. I think almost never in math. I can't even think of any time in math you use this term, but in physics, I think it's very common. Okay, so the resultant of a 10-pound force and another force. So we have two forces adding up to be equal to this resultant, all right? So one of the forces that adds up to the resultant being equal to the resultant is 10 pounds. So let me draw a picture, and for these problems, you'll probably want to draw pictures because they really help you figure out what information you know and what information you want to know. And then from there, you can often quite easily, actually, once you're used to it, figure out how to get from what you know to what you don't know. All right, so let's draw this. So we've got the resultant of a 10-pound force and another force. So we've got a 10-pound force. So 10-pound force means its magnitude is 10, all right? And of course, when we're talking about forces, especially in 2D or 3D, these are all vectors, all right? So this 10-pound force is represented by a vector of length 10 in a certain direction, all right? We don't know what direction it is. Okay, so the resultant of a 10-pound force and another force, so I'm going to draw this other force right there. We don't know how big it is actually right now, but we know the resultant has a magnitude of 12 pounds, all right? So let me draw the resultant, and again, the resultant is the sum of these two forces, and so I'm going to draw the sum using the geometric way to draw the sum of two vectors. And so here we have the resultant is this middle guy right there. Okay. All right. We're told that the resultant of a 10-pound force and another force has a magnitude of 12 pounds. So the resultant is the one that has the magnitude of 12 pounds. All right. So one thing here, you definitely want to read these problems very, very carefully. Because I think, especially for this problem right here, it's very easy to make a mistake and think that you're adding a 10-pound force and a 12-pound force, but that's not what's going on. It's saying the resultant of these two forces has a magnitude of 12 pounds. All right. So this guy is 12. So the sum of the first vector and the second vector has a length of 12. All right. So the resultant has a magnitude of 12. All right. At an angle of 20 pounds with the 10-pound force. All right. So again, this is the resultant that has an angle of 20 pounds with the 10-pound force. And so this angle right here right there is 20 degrees. All right. Okay, and again, you want to read these very carefully because different problems will have different setups. For this problem, this is our setup, but in a different problem, instead of giving you the length of the resultant, maybe they would give you the length of the second vector, right? Instead of giving you the angle between the resultant and the first vector, they might give you the angle between the first vector and the second vector. So you definitely want to make sure you read these problems very carefully. They could give you, the information they give you will vary from problem to problem. All right, so we'll do another example of this kind of problem, and we'll see exactly that, that situation. Okay, so find the magnitude of the other force as well as the angle between the two forces. So the magnitude of the other force, so the other force would be this guy right here. So we want to know the magnitude of this force, all right? And we want to know the angle between the two forces. So that would be this angle, full angle right there, all right? So those two are the bits of two bits of information that we need to figure out for this problem. Okay, let's see. So the way we're going to do these problems, again, we're focused on doing these kind of from the trig point of view. So the way I'm going to look at it is that we have two congruent triangles. Oh no. Okay, sorry. We have two congruent triangles. How do I change? Here we go. Okay, so we have two, congruent triangles, one right here, right? This triangle up here, and then this triangle down here. Okay, they're congruent because this side right there is the same as that side right there, right? Because when we do this addition of forces, right, the way we, or of vectors, the way we add is we draw these two parallel vectors, all right? And then and again, also these two, the question mark vector here is the same as that one there, okay? And then of course they share a side. So these two triangles are congruent because they share side lengths, right? Side, 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 if you remember from kind of high school geometry. So these two triangles are congruent. Why do we care about that? Well, that means that, first of all, this question mark right there, the length of this vector right here, is exactly the same as the length of this blue dotted line up here, all right? So this guy is as well question mark, okay? And I want to think of it this way because I want to work with triangles because I know trig, and in particular, I know the laws of sines and cosines, and that's what we're going to use to solve this problem, all right? So I want to think in terms of triangles. And again, the way the problem's given, right, you're not given a triangle, you're given three vectors like this, but once we kind of create this triangle, we're able to kind of use the knowledge that we've learned, okay? All right, so that's our idea. So now I'm going to focus myself on this upper triangle, right? And also, I guess we should note that this second question mark, the angle that we want to know, we can also phrase that in terms of our triangle up here, okay? So what we notice is because our two triangles are congruent, this guy being 20 degrees, right? So this angle right here is the angle that's between the side of length 10 and the side of length 20, all right? So for the other triangle, we know that this is also length 10, right? So because it's a parallel vector. And so this is the side of length for the second triangle, the lower triangle. This is the side of length 12. That's the side of length 10. And so the angle that's 20 degrees is this guy right there. All right, so I know this guy here is 20 degrees as well. All right. Okay. Why do I care about that? Well, this question mark right here, question mark is equal to, let me write it like this. So the size of this angle, it's 20 degrees plus the size of this angle right there. right? And let me give that one a name. Let me call this theta. All right. So it's 20 degrees plus theta, right? Because it covers both of these angles right here. All right. That theta looks weird. Let me put it right there. 20 degrees plus theta. All right. So if this guy here is theta and that guy there is 20 in the lower triangle, that means up here, this angle here must be theta. All right. Okay. So in essence, if we want to know this question mark angle, we only need to figure out theta, right? And then once we add 20 degrees to it, we know the question mark angle. Okay, so essentially the problem becomes, what is this length right there? And what is this angle theta? All right. Okay, so this picture is getting a little messy, so let me only draw the top triangle and write down all the information that we know, and take a look from here. So we know this side length is 10. We know this side length is 12. We know this angle here is 20 degrees. We need to know this angle here, right? And we need to know this length right there. Okay. All right. Well, we have a triangle. We have 3 bits of information, this side, this angle, and this side, right? So this is exactly this kind of situation where we can use the laws of cosines or the law of sines to solve the problem, right? 3 bits of information exactly to set up for those law of sine and cosine problems. Okay, for this particular problem, we're going to want to use, or the easiest way is to use the law of cosines because we have the side, the middle angle, and a side, right? And so we know the law of cosines is instantly going to give me this question mark right there as the third side, right? In particular, question mark squared, just writing down the law of cosines, is equal to 10 squared plus 12 squared minus 2 times 10 times 12 times cosine of 20 degrees. Okay. And so we're all set, right? So question mark is equal to square root of that. And now of course we don't know how to calculate 20 degrees by hand, so we can use a calculator at this point here. All right. So this is what you would want to do for example, in the online homework. So let me write, so question mark is equal to 10 squared plus 12 squared minus 2 times 10 times 12. And let's just leave it like that, 2 times 10 times 12 cosine, of 20 degrees, square root. Okay, so that would be, whatever this is, that would be an answer to the first part of the question, which was find the magnitude of the other force. Okay. All right. The second part of the question was the angle, and we've already said that as long as we can figure out this theta, right, we just add 20 degrees to it and we've got the angle that we need. So again, this is we just continue the problem of solving the triangle, right? How would we get this angle theta? Well, we just do as if this was a law of sines or cosine problem, and we know that now that we have this question mark here, we can quote the law of cosines based on this angle, right? So the opposite of this angle is 10, so we would be looking at 10 squared equals 12 squared plus question mark squared. And an important feature here is we know question mark, right? We can plug it in from the calculator at this point. And then minus 2 times 12 times question mark times cosine of theta, right? And then in order to get theta, we throw everything to the other side and take an arc cosine. So cosine, let me do it in a couple steps. 2 times 12 times question mark times cosine theta is equal to 10 squared minus 12 squared minus question mark squared. And so cosine theta is equal to 10 squared minus 12 squared minus question mark squared all over 2 times 12 times question mark. And so theta is arc cosine of this business here. And again, at this point, you would need to use a calculator. But again, there's no issue here because everything inside this arc cosine is known. As in particular, the question mark is known. All right. Okay. One thing to note. I chose to use the law of cosines in order to get this angle theta. Oh, sorry. Let me just write out the final. So angle that we want is 20 degrees plus theta. All right. So whatever theta happens to be. Okay, because of course, remember the angle that we actually want is this this full angle here. Okay, so it's not just theta. All right, let me make a comment about using law of cosines. So I used the law of cosines to get theta. Alternatively, what you could have done was use the law of sines, where you're looking at sine of theta over 10 equals sine of 20 degrees over question mark. Okay, that would work. You could throw this 10 to the other side. Sine of theta is equal to sine of 20 degrees times 10 over question mark, right? And then you could take arc cosine or arc sine on both sides. That's your strategy. This would work because you know theta, right? At this point of the problem. I don't like this very much compared to using the law of cosines, because once you take the arc sine, remember that for triangles, there's actually potentially multiple solutions to this problem, this problems right here, right? Because there's potentially two solutions to sine theta equals this business here that are between 0 and 180 degrees. And so there's potentially two solutions, and then you'd have to go about and figure out which solution is the one that you want, right? Because if there are two solutions, one of them is not the one that you want. However, with the law, when I use the arc cosine, I don't have that problem, because arc cosine, because this problem right here only has one solution between 0 and 180 degrees. All right, so that's why I always prefer to use the law of cosines over the law of sines when I'm doing when I have a situation where I have to take the inverse trig function, right? Because again, inverse trig function of cosine with regards to triangles is going to give me a single answer only, whereas inverse trig function with sine will give me one answer, but I also have to consider the other answer, which is a definite possibility. All right, so that's why I did this entire problem with the law of cosines. Okay. Oh, actually, let me take a quick look here. I think this is did I do this algebra right? I threw this to that side. I threw these to the other side. I think actually there should be a minus sign right there, and so that means there's a minus sign right in front here. Sorry about that. Minus sign right there. Okay. In any case, actually, I should probably just give you the answers as numbers also. So it turns out that if you actually plug these into a calculator, let me draw the picture again. So the length, so this was 10, this was 12. So it turns out that the length of this second vector, so if we plug, where is it? This guy into a calculator, we're going to get something like 4.3, roughly 4.3. And this angle here is going to be, or let me write, the angle that we found is going to be something like 52.7 degrees. And so the full angle that we're actually looking for is going to be that plus 20 degrees, so 72.7 degrees. Okay. All right. So that's how we do this problem. Let's do one that looks very similar, but where the information is slightly different. So this is a nice problem. You'll see one on your homework that's like this. So I guess I'm not going to write a huge description here, so let's just kind of say it out in words. So we've got, I think on the homework it's a donkey or something like that. So we've got a donkey here. We've got ropes around the neck of the donkey, and we've got a person pulling. So this is a view from above. We've got a person pulling on the rope in this direction. In this direction, with a force of, let's say, 50 pounds. All right, we've got another person pulling in that direction with a force of 70 pounds. All right, and let's say the angle between the two people, so this is person number one, this is person number two, the angle between the two people is, let's say, 35 degrees. All right, so we've got these two people. They're pulling, so I guess I should put arrows here, right? This person is pulling in that direction. This person is pulling in that direction, right? So this is actually a vector problem, right? This vector is pointing in that direction, 50 pounds, and this one is 70 pounds in that direction. Now, the donkey, let's say, doesn't want to move. So the donkey wants to resist this pull. And so the question is, how much force should the donkey resist with in order that it doesn't move? Okay, so of course, one thing to note is that the donkey can kind of resist in different directions. So when we say resist, what we mean is the donkey is kind of pulling backwards, right, away from these two people with a force, with a certain amount of force, right? So it wants to pull back with the perfect amount of force and in the correct direction so that it doesn't move. Okay, and we're assuming for these problems that the donkey knows which direction to pull against, right? Which is not that unusual, because ultimately the donkey is being pulled in it's being pulled in two directions, but ultimately the donkey feels this as a pull in a single direction, and so it just has to resist in the opposite direction. Okay, and that actually hints at how we do this problem. Because the way the donkey feels the overall force that's being pulled, overall as in, from person one and from person two together, that's going to be the resultant of these two forces, all right? So the force that the donkey feels is going to be the sum of the two forces that we have here. And so the force the donkey feels is going to be that force right there, okay? All right, so what does the donkey need to do so that it doesn't move? Well, it's feeling a force in this direction overall, right? With this length. So if it resists in the opposite direction, directly opposite to the resultant here, with exactly the same length as this resultant here, then it won't move at all. All right. So another way to say this is, if I have F1 here as force number one for person one, F2 here for force number two, right? And then let's do F sub D here for force of the donkey. What we need is actually force sub one plus force sub two plus F sub D has to be 0, right? So what this means is the overall force felt by the donkey, which is the force, from person one, the force from person two, the force from the donkey itself, right? All of these have to be 0, add up to 0, and that would mean that the donkey feels no force. So overall, the donkey does not move. Okay. So what that means is, of course, that if you look at it this way, that means F sub D should be equal to F sub 1, let me write like this, minus F sub 1 plus F sub 2, right? And that's exactly what the description that we've given in terms of pictures is telling us, right? Because this one right here, this vector right here, the resultant is F sub 1 plus F sub 2, right? This guy right here is F sub 1 plus F sub 2. And so, of course, when we said the opposite direction, that one is minus F sub 1 plus F sub 2, right? Minus of the whole thing. Okay. All right. So ultimately, what we need to figure out is the length of length of this vector right there, all right? Because we just want the magnitude, okay? All right, there's actually not, I haven't given enough information in this problem for you to tell exactly which direction the donkey should be opposing the force with, right? But we can figure out the magnitude. Okay, so again, we need to figure out this length right there. Right? I guess let me put a question mark right there. That's what we need. Okay, so let me draw the picture again because that one's getting a little messy. We've got 50-pound force here. We've got a 70-pound force here. All right, let me just write the math. And then we've got 25 degrees here. We have parallelogram like this. This is the side length that we actually want. The 25 is actually the entire angle from here to there. All right. Okay. So again, because this middle vector is the resultant of the other two vectors, is the sum of the other two vectors, we have a parallelogram here, right? Because that's how we add vectors, which means again we have two congruent triangles, right? And again, we have that this length is 50, that length is 70. And again, essentially, we're asked to solve this triangle here. Okay. All right. Oh, and I guess this 25 degrees, we're going to have to figure out how to deal with that as well. Okay. So how do we work with this 25 degrees? Well, this 20, let me give two names here. So let me call this angle here, let me call that alpha, all right? Let me call this angle here, let me call that one beta, all right? So we know that alpha plus beta is equal to 25 degrees, all right? And we just said that these two triangles are congruent. And in our discussion above, we said that this angle here has to be the same as that angle there, all right? So this angle here has to be beta, okay? Now this problem, notice, is a little different because we actually don't know what alpha is, like we did in the last problem. But it's okay because what we see from this picture is, let me draw it again, just a triangle now, because we've kind of, at this point, we've ported all our information to just a single triangle, right? This guy here is 50, this here is 70, this here is alpha, this here is beta, this here is the side that we want. And we know that alpha plus beta is equal to 25 degrees. All right. Okay, now this looks kind of unworkable because we don't know any of the angles, but we actually do because alpha plus beta is 25 degrees. But if I call this guy up here gamma, we know that alpha plus beta plus gamma have to be 180 degrees, right? And if alpha plus beta is 25 degrees, that tells me that 25 degrees plus gamma is equal to 180 degrees. And so gamma is equal to 180 degrees minus 25 degrees, which is 155 degrees. Okay. So actually, we do know the angle. We know, we know not these angles down here, but we know that top angle there. All right. So let's update our information. We know this is 50. This was 70. This is 155 degrees. And we need to know that side right there. Okay. So again, most of these problems are essentially getting the information from the words to a picture, and then at least certainly for this type of problem, figuring out the triangle information that you know, right? In this case, we know this side, we know the middle angle, and we know that side. And then realizing what information you need to know, which is this opposite side here. All right. And once we see this, again, just, again, circling the pieces of information that we know, we instantly see that we want to use the law of cosines. And so we have question mark squared, law of cosines based on the angle 155 degrees. Question mark squared, which is the opposite side, is equal to 50 squared plus 70 squared minus 2 times 50 times 70 times cosine of 155 degrees. All right, guess I don't need parentheses there. All right, and we're all set, right? So question mark is equal to 50 squared plus 70 squared minus 2 times 50, 7,000. Let me just write it like that, I guess. 7,000 cosine 155 degrees. Okay, again, just by taking square root of both sides. And again, normally you have to pop out a plus or minus, but we're talking about actual physical things. The length of a vector should be a positive number, so we toss away the negative solution. Okay, and that's it for this problem. We only needed the magnitude of the force that that the donkey has to resist with. But again, notice that because we have this information, if we needed to, if the problem had asked us, we could actually figure out all the rest of the information, right? We could figure out this, we could figure out this. Okay, so you'll see a few problems like this on the homework. And again, some of them might look very, very similar to this, but I believe there's at least one which has where the information they give you is slightly different, right? So again, read the problems very, very carefully and draw very careful pictures if you can. All right, a second type of problem you'll see in this section. By the way, we'll be talking about, in a way, 3 different types of problems, but in reality, of course, vectors can be used all over the place. And so there's actually an infinite number of kind of variety of problems that can be solved with vectors. We're just doing a small tasting of kind of the possibilities for our class. All right, so the next kind of problem we want to solve are ones where we have an incline of some sort, like this. Let's say a hill, right? We've got a hill in the shape of a incline like this, and we have an object on this hill, right? What's going to happen is, again, we're assuming there's no such thing as friction, just for simplicity's sake. What's going to happen is this object is going to start sliding downhill. All right. Now the question is, how does it slide downhill, right? For example, if I want to resist this slide downhill, if I don't want it to slide downhill, right? How would I do that? I would stand here, and I would need to push it in the opposite direction of its motion. I would need to push it that direction, right? And one typical question would be, how hard do I have to push to prevent this thing from sliding downhill? All right, to resist this thing from sliding downhill. And this kind of problem boils down to the fact that the object wants to slide downhill because gravity is pulling it downwards, right? So if an object is, so let me say for this problem, the object is 100 pounds. 100 pounds. What we mean by that is that the force of gravity pulling downwards towards the center of the Earth, so pulling downwards like this, right, vertically downwards, has a magnitude of 100. All right, so this length right here is 100. Okay, so when we say something is 100 pounds, right, that means the force of gravity is pulling at it at a force of 100 pounds. And where is it pulling? It's pulling straight downwards. Okay. All right, so this is where the kind of vector idea comes in, right? We have a vector. The force of gravity is represented by a vector of length 100 in the direction directly downwards. Okay, now how much force do we need to push back to prevent this object from moving? Well, not 100 pounds. We don't need to push back with 100 pounds because what's happening is gravity is pulling downwards like this. But if you kind of break this gravity vector down into two parts. So let me put this 100 on the other side. So I'm going to put this 100 right here. And then what I'm going to do here is I'm going to break this gravity vector down into two components. One component is perpendicular to the hill, perpendicular to the incline. All right. So this component right there. Okay. So this one, again, very, very important that this guy is perpendicular to the incline, to the hill. All right. And then another component like this. All right. And it's very important that this guy should be a right angle. Okay. So let me draw arrows here. Let me draw an arrow right there and an arrow right there. Okay, so what I've done with these two arrows is I've said that the force of gravity, which is this 100 length vector pointing straight downwards, that's equal to the sum of this first vector here that's perpendicular to the incline, plus this second vector right there that is actually, it's parallel to the incline. All right. Okay, now why do we do this? The idea is that gravity is pulling at a force of 100 pounds straight down, but some of this force is in effect, when it comes to the motion of this object, is being wasted, right? So this portion of the force that's pulling perpendicular to the incline, that is not contributing to the object sliding downwards. All right. So the amount that the object slides downwards in a way is determined only by this guy right there. Okay. So this, this component here has nothing to do with the sliding of the object. All right. If you want, you can think of this component as keeping the object on the hill as opposed to just floating away into space. All right. So again, this vector here, right, that's parallel to the incline, the portion of gravity, of the force of gravity, that's parallel to the incline, that's the amount of force that the object is kind of sliding down, sliding along the hill at. So in order for me to stop it sliding downhill, I need to resist with exactly the equal amount of force in the opposite direction. All right. So I need to push this object in exactly the opposite direction, right, which is again parallel to the incline. And the amount of force I need to push with is exactly that length right there. Okay, so these two lengths have to be the same. So in essence, the problem is, of me trying to keep this object from sliding downwards is asking what is the length of this side right there. All right, where we have in this setup, again, this is a right angle, and that guy is a right angle as well. Okay. Okay, so that's the general idea of this problem. Again, for different setups, you might be given different portions of the information. You'll see a problem on homework where they give you how much you have to push against, and you have to figure out how much the object weighs, right? In which case you have to figure out this size right here. It won't be given to you, and so on. Okay, I think there's another problem, if I remember correctly, where you have to figure out the angle of the incline. Okay, so for this problem, actually, I almost forgot to mention, we're told this hill, let's say, has an incline of 20 degrees. Okay, so we actually have to know this for this problem. All right, so again, on another problem in the homework, you'll be given perhaps this 100 pounds. You'll be given how much you have to push, how hard you have to push to resist the object from sliding down. And then the question would be, what is the angle of the incline? Okay. Okay. So how do we do this problem? Again, probably a better way to do this problem is to work natively just with vectors. And you'll likely do that if you do a more advanced math or physics class. But again, we're focused on trig. So we're going to solve this using trig. All right. Okay, so the first thing to notice is the side that we want, this length right there, is the one side of a right triangle, right? Because this guy here is a right angle. And not only that, we know that this right triangle has hypotenuse equal to 100, right? The side opposite the right angle would be the hypotenuse. Okay, so let me, and before we draw the right triangle by itself, this is, what I just said is not enough information to figure it out. I need this 20 degrees, all right? So how does this 20 degrees come in? Well, if I extend this ground horizontally like that, right? What I see is another right triangle like this, okay? And what I have is a right triangle right there. If this side here, this angle here is 20 degrees, that angle is 90 degrees, so that means I know that angle right there, right? This angle right there, okay? So this angle right there has to be 70 degrees, right? In order to make the whole thing 180 degrees. Okay, however, this guy right here is a right angle, right? Because again, it's very important that this guy right there be perpendicular to the incline. So this angle here was a right angle. And so, of course, that means this angle is a right angle, right? We already know that this side is 70 degrees. And so this side right there has to be 20 degrees. Okay, so ultimately, this 20 degrees tells me that this guy is also 20 degrees. All right. Okay, so let me just draw the right triangle that I care about, this one here by itself. So what I know at this point is I have a right triangle. This guy is 100. This guy is the guy I want to know. That guy right there is, oops. That guy right there is 20 degrees. All right. So that's, sorry. What's going on? That's this triangle. So this triangle right here is that triangle right there. Okay. All right. And now we can solve the problem because this one is just a right triangle problem, right? And so we don't even have to use the law of cosines or anything like that. We know that opposite over hypotenuse is the sine. So sine of 20 degrees. And again, we're only allowed to do this because we know this is a right triangle, right? So sine of 20 degrees is equal to question mark over 100. And so question mark is equal to 100 sine 20 degrees. All right. And if we want to use units, our answer would be 100 sine 20 degrees pounds. Right? That's how much force we have to resist in order to prevent this object from sliding downhill. All right. And of course, at this point, you can plug this sine 20 degrees into a calculator, multiply it to 100, and that's how much force you have to exert. Okay. Let me notice something. In this particular problem that I did, this was 20 degrees. Let's say it was just a generic angle theta, right? Generic angle theta here. Then what would have happened was, would be that this 20 degrees would be a theta, and our final answer would depend on sine of theta. All right, so whatever this incline of my hill is, right, however steep this hill is, the amount of force I would have to exert to prevent the object from falling down or from sliding downwards would be 100 sine of theta, all right, pounds. So I want to take a look at this because let's see if this answer makes sense in terms of physics, right? So let's think about this. If the incline were 0 degrees, right? In other words, if this theta were 0 degrees, what would happen? Our picture would just be a flat hill, right? A flat ground, right? Because 0 degrees. And so our object would be here. And what would happen is gravity would pull straight down like this, and our object wouldn't move at all, right? There's no sliding because there's no hill, right? And so I expect that my answer should be, in order to prevent this thing from sliding, I don't have to exert any force because it's not sliding at all anyway, right? So let's check that with our answer, our generic answer up here. Well, when theta is 0, sine of theta is sine of 0. Sine of 0 is 0. And so that kind of fits with our physics intuition that the answer should be 0, right? Okay, and let's go the other way as well. Let's say the angle theta were 90 degrees, right? So like this, the object is right there, right? And it's being pulled down by gravity, again, straight downwards this way, right? Okay, what would we expect? How much force would we expect that we would have to exert in order to prevent this object from moving? Well, in this situation, because the incline or the hill is at 90 degrees, right, it's actually not kind of resisting this object at all, right? It almost has nothing to do with whether this object is falling or how fast this object is being pulled downwards or how strong this object is pulling downwards. So in essence, what's happening is if I want to resist this thing from falling, I have to I have to resist the entirety of gravity, right? I have to push upwards with as much strength, with as much force as the weight of this object. Okay? Because again, this incline is actually irrelevant in this situation, in the theta equals 90 degrees situation, right? Okay, so because this object weighs 100 pounds, then I expect in this situation, the answer, just arguing kind of in terms of physics without any math, I expect the answer should be I need to resist using a force of 100 pounds, right? Which makes sense because, you know, if I want to hold up an object to prevent it from falling, and if that object is 100 pounds, then I have to, you know, use a force of 100 pounds, right? The hill is not helping me at all here. And if I look at this, our generic answer up here, if I stick in 90 degrees, sine of 90 degrees is 1. And so my answer would have been 100 pounds. Okay, so this answer of 100 sine theta makes perfect sense. All right. Also, of course, you can see that sine theta is less than 1, less than or equal to 1. And so normally, right, if there is an incline of something degrees, right, 15 degrees, the amount that I have to resist would be something less than 1 times 100. So I'm always, or generically, if there is an incline, I have to resist with a force of less than 100 pounds, right? Because it'd be ridiculous if I have to resist with a force of more than 100 pounds when the object only weighs 100 pounds itself. Okay, so everything makes perfect sense when you think about this in terms of both physics and the mathematical formulaic answer. All right. Okay. So again, you'll see problems in the homeworks where you have to kind of work it, where they give you different bits of information, but the generic picture is always this same. You have this, you have the force of gravity, you have this incline angle here, and ultimately it's equal to that angle right there. Ultimately, you have this right triangle right here, and ultimately the amount that the object, how much force the object is sliding downwards with is that length right there. Okay. Where this part of the force is doing nothing. Okay, so the last type of problem that we're going to talk about are problems. So both of these two problems that we just talked about were force problems, where we think of vectors representing force. But we said in our introduction to vectors that vectors can represent velocity as well. So let's do an example of that kind. So a typical setup here would be you have a river. Let's say this river runs east to west, or not east to west, but left and right, east and west. All right. Let's say it actually flows west to east. Okay. So this river flows this way. And of course, for simplicity, let's assume this flow is at a constant rate. All right, let me give some numbers. So let's say this flow is at a constant 10 meters per second. All right, so 10 meters per second everywhere. If you want to kind of study the flow of kind of more realistic river, where it could be 10 meters per second here, 5 meters per second there, then you'd have to do more advanced math. So our river, 10 meters per second everywhere. All right, 10 meters per second, and so on. Okay, let's say this river has a certain width, right? So the distance from one shore to the other shore, or one bank of the river to the other bank. Let's say this distance is 1,000 feet, or we're using meters. So let's say 1,000 meters. Okay. All right. Now the setup is something like this. I'm right here, and I'm in a boat, and I want to get to the other side of the river, right? Let's say I can row. So here's my boat, right? I can row my boat at a rate of, let's say, 10 meters per second. Okay. Okay, so if I row from the starting from the south bank, so I guess technically that would be called the right bank of the river, because the river is flowing from from west to east. So this side would be the right bank, that side would be the left bank. Okay, anyway, starting from the south bank, south maybe is more descriptive for this particular problem. If I row starting from the south bank due north, right? So I'm rowing directly north. All right, so I'm rowing this way. All right. Number one, how long will it take for me to reach the other end? And number two, which is the more interesting one in terms of trig, which is how far down the river will I end up? Okay, so this one's kind of interesting because if we think about this, if I'm pointing my boat north, right? So that's what's going on here, right? Heading due north, right? So I'm pointing the nose of my boat north, and I'm rowing in that direction. The river is also pushing me from west to east. So my actual motion is not going to be upwards. It's going to be a combination of upwards and to the right. All right. So overall, my motion is going to be something like that, right? So by the time I hit the shore, I'm actually going to end up somewhere down the river, right? I'm not going to end up there. I'm going to end up somewhere here. Okay. So the question is basically, where is there, right? How far down the river am I actually going to end up? Okay, so we actually need part one to figure out part two. Part one has nothing to do with trig. How long will it take? Well, if I row at 10 meters per second, oops, and I need to row, so I'm rowing 10 meters per second north, right? And I need to travel 1,000 meters north, right? So north to travel, so I'm rowing 10 meters north to travel, 1,000 meters, right? Need to row for 1,000 over 10 seconds, right? Okay, and this makes sense. If we just check our units, 1,000 meters over 10 meters per second, that's 1,000 over 10 meters, and then seconds over meters, and the meters cancel, so we get 100 seconds. Okay, so that makes sense in terms of the units. Okay, so we need to row for 100 seconds. All right, so that's how long it takes for me to get to the other end. So now the question is, where do I end up? Well, 100 seconds, I am being pushed from left to right, from west to east, at a rate of, where's my rate? At a rate of 10 meters per second. Right? Maybe I should have used different numbers, but it's okay. I'm being pushed from left to right at a rate of 10 meters per second, right? So how far am I going to be pushed? Well, over 100 seconds, if I'm pushed to the right at 10 meters per second, then I'll travel to the east 100, sorry, let me write like this, 10 meters per second. 10 meters per second for 100 seconds, and that would be 1,000 meters, of course, as expected. Okay. Maybe this is a little confusing. Let me change the numbers up here just a little bit. Let me make this river flow at 20 meters per second, 20 meters per second, just so that, we don't have these 10 meters per second everywhere. So this would be 20. Okay. So it would be 2,000 meters here. All right. So what's happening, of course, is I'm rowing north. By the time I get to the north shore, the river will have pushed me to the east a whole bunch. How much? Well, it took me 100 seconds to get up to the north bank. And in that 100 seconds, the river pushed me 20 times 100 meters to the east. Okay? So we can choose to do the problem this way. If you want to think about it in terms of vectors, what's happening is we have, I'm rowing 10 meters per second, 10 meters per second north, and the river is pushing me 20 meters per second east. So my overall motion, or my overall, velocity is going to be the sum of these two vectors. All right. So the direction in which my boat is actually moving is that direction right there, right? The sum of these two vectors. Okay. And so if we write this in terms of our vector notation, that would be 20 comma 10, right? That would be this vector right there. Okay. So if that's my velocity vector, where am I going to be at any point in time, right? So if this is the origin right there, at any point in time, I'm going to be at the position. So at time t, I'm at position 20t comma 10t. Okay. So for example, after 1 second, I've rowed myself 10 meters north, and in the same time, the river has pushed me 20 meters to the east. So I'm at 10 comma 20, right? In another second, I will have rowed another 10 meters north, and the river will have pushed me another 20 meters to the east, right? So I'll be at 20 comma 40, which is, I'll be at 40 comma 20, which will be 20 times 2 comma 10 times 2, right? So this is my actual position at any time. All right. So we can actually answer the questions from here. How long does it take me to reach the other shore? Well, that would be asking when is 10t equal to 1,000, right? That's the same as asking when will I reach other shore, right? Because other shore is, let me write it down here. The other shore is at position 1,000, right? In terms of the y position. And anything can be the x position, right? So it's asking when 10t is equal to 1,000. And of course, that means t equals 100. And in that time, how much, where will I be? How far will the river have pushed me to the east? Well, if over at time t, my easterly position is given by the x-coordinate, right? So if it took me 10 seconds to row north, the water will have pushed me 20 times 10 to the east, right? So if I row for 5 seconds north, then the water will have pushed me 20 times 5 meters to the east. Okay, so the sum of these two vectors tells me, gives me kind of a formula for my actual position at any time. All right, so that's maybe a more vectorly point of view for this problem. Okay, so one final kind of secondary question here is, in the same setup, right? So this river is pushing, I think it was 20 meters per second, and I can row my boat at a rate of 10 meters per second, all right? The question is, what if I start here and I actually want to end up on the opposite side exactly in the same position, right? I want to end up here. So that means that I would have to row in a direction something like that, right? Because, well, first of all, I have to row in a somewhat northerly direction so that I can actually reach the other end. But I also have to row west in a westerly direction because the river is pushing me to the east. So I need to kind of, in a way, time it perfectly so that as I row to the west and as the river pushes me to the east, overall, I reach the other side exactly at the correct position. Okay. All right, so how do I figure that out, right? What exactly is the direction that I have to row in? Well, let's see. So if I call this direction that I'm rowing in a comma b as a vector, right? My overall motion is going to depend on my motion, my rowing, and the river, right? The river is pushing me 20 meters per second to the east, so I'm going to represent that as the vector 20 comma 0. All right. So my overall motion, as we said earlier, is the sum of these two. So our velocity vector is AB plus 20, 0, right? Which is just A plus 20, comma B. Okay, so we need to figure out A and B so that, right, we end up on the other side of the shore exactly in the correct position. All right. Okay, so this is our velocity vector. If we call this our starting point 0, comma 0, so our position at time t is going to be a plus 20 t, comma b times t. I'm going to do parentheses here to mean position. All right. So this is our position at time t. Okay. So how do we figure out A and B? Well, we know that we row at 10 meters per second, right? So what that means is the length of this vector, the magnitude of our velocity vector, our rowing velocity, is 10. All right. So how does that relate to the A and B? Well, that's the length of the vector. So that means A squared plus B squared has to be equal to 10 squared, right? So that gives me one relationship that helps me figure out what A and B should be. All right. So the other relationship that we're looking for, actually, so the other bit of information relevant to this problem is that we want to reach the other end at exactly this position right there, right? So if this position, if we're using coordinates, this position is 0, comma 0, right, the origin, then that position right there, we said our river was 1,000 meters wide. So that position right there is 0, comma 1,000, right? And so if it takes time capital T to hit the other side, to get to the other side, to get to the other side, then what are we requiring? That means that a plus 20 capital T, right? This guy right here, our x coordinate position when we hit this. So this is our x coordinate position when we hit the other side, right? That should be equal to 0, right? Because our x coordinate position when we hit the other side should be 0. Okay. Also, our y coordinate position at the other side, well, it's 1,000 meters to the north, right? So B capital T, has to be 1,000. Okay. In other words, in terms of kind of a position point, right? When we hit the other side, where are we? We're at a plus 20 capital T, comma B capital T, right? Again, where capital T is the time it takes to hit the other side. And again, this has to be 1,000 because we've hit the other side. And this has to be 0 because we're demanding that the way we row, we hit the other side exactly at position, x position 0. Okay? And so ultimately we have 3 equations and we have 3 unknowns. So we have 3 equations, this one, and this one. And we have 3 unknowns, a, b, and the time it takes, capital T. All right, so 3 equations, 3 unknowns. The general idea in mathematics is that this means generically there will be a finite number of solutions. And so we just do algebra now to figure out those solutions. All right, so there's a lot of ways we can approach this. Actually, let me write them all down together just to have them all combined or have them all kind of visible. Okay, I just realized why I set up the problem originally with the 10 meters and the 10 meters. And I probably shouldn't have just arbitrarily changed the speed of the river because we're not going to be able to solve this problem, at least the way I've set it up. So here's what happened. Originally, I had the problem set up as the river flowing 10 meters and we could row 10 meters. Well, actually, that wouldn't have worked either, now that I think about it. So the problem is that, see, this middle equation, I'll fix the problem in 1 second, but let me explain this. So this middle equation here tells me that a plus 20t equals 0, right? It's not going to take 0 time to reach the other side. So t is not 0. So that means a plus 20 has to be 0, right? Which means that a plus 20 has to be 0, which means a has to be equal to minus 20. Okay, but that's a problem because, sorry, this had to be 1,000. If a is minus 20, a squared plus b squared cannot be 100, right? Because a squared would already be 400. Okay, so plug it back into here. We would get a squared plus b squared equals 100. That would tell me 20 squared plus b squared equals 100, which tells me b squared is equal to minus 300, right? But we certainly can't have that. There's no solutions, right? And so what actually this tells me is that it's not possible for me to get to the other side in exactly the same position right there, all right? Because the river is flowing too fast compared to how fast I row, all right? And that makes sense, right? Because I can only row 10 meters per second. The river is flowing at 20 meters per second to the east. And so I essentially don't have enough strength to overcome that 20 meters per second to the east, right? So no matter what I do, no matter what direction I row in, I'm going to end up downriver as opposed to directly across. Okay. So probably what so this is still a good problem because we've realized, through these equations that we cannot do what we want, right? So we're going to have to get a motorboat, right? Or work out and get stronger and row faster. Okay, so if we do that, then what would happen is, let's say the river stays the same, but we've gotten stronger, and let's say we can row faster now, and instead of 10 meters per second, we can now row at 30 meters per second, right? So let's change that guy right there to 30 meters per second. Okay. So what would happen is the only thing that would change in this problem is that this 10 squared would be a 30 squared. Okay. Because 30 meters per second means the length of our velocity vector has to be 30, which means a squared plus b squared has to be 30 squared. Okay. All right. And so what would happen here is that this would be 30 squared, right? And that would be 900. Okay. All right, and so what would happen is this middle equation would tell me that a would have to be minus 20. And so when we put that back into equation number 1, that would mean that a squared plus b squared would have to be 900, right? And so 20 squared plus b squared has to be 900. And so b squared would have to be now a positive number, right? 20 squared is 400. And so 900 minus 400 is 500. Okay, so in this case, b would be 10 root 5. All right, and so this would tell me that I need to row in the direction, so a was minus 20, so minus 20, comma, and then b is 10 root 5. All right, so that's the direction in which I need to row. All right. All right. Not only the direction, but this is actually the velocity vector of my rowing. All right. And if we were asked how long it takes to get to the other side, well, BT has to be 1,000, right? So how long to get to other side? Well, BT has to be 1,000. We know B is 10 root 5, right? So 10 root 5 T is 1,000. And so T is equal to 100 over root 5. Let's rationalize that. So this is going to be 20 root 5 seconds. Okay. So we can still answer the question just as before. We know exactly what direction we need to row, and we know exactly how long it takes to get to the other side. All right. Okay, and if you think about, so I did this very, very mathematically, but if you think about this kind of in terms of, the physics or the physical aspects of what's going on, the fact that a equals minus 20 makes perfect sense, because what I'm asking for is for the river to essentially not be pushing me, right, as I go forward. So at every position on the river, right, my x component of my velocity has to completely oppose that 20 meters per second, right? So again, the river is pushing this way, 20 meters per second. I need to, in terms of my boat, needs to be pushing back 20 meters per second that way, right? So I need to be rowing at a velocity vector of minus 20 comma something. All right. And that something, right, is going to be determined by my overall rowing speed, right? So 20 squared plus that thing squared should be my overall velocity, how fast I row, right? And then that allows me to solve this guy here. Okay. All right, so again, everything makes sense if I think, in terms of both the physics and in terms of just pure mathematics. All right. Okay, so that'll be it for this section. If you do look at the book, you'll see a couple other varieties of problems that are similar. It'd be a good idea maybe to take a look at them to see if you can parse the words and put them into math. because that's a skill that I feel a lot of students have trouble with, going from the words to the picture, or words to kind of the information that you know and the information that you want. So even if you don't decide to do all the problems, at least kind of set them up from the words to the picture so that you're comfortable parsing that information.